Well, look at you. You came back, and you're ready to learn more about ion chromatography, and you've not quit on me. Well, let's wait until we get ready to use the instrument, and then you can decide whether or not you're ready to quit on me. So, we started talking about ion chromatography, and we abbreviated that with an IC, and I gave you a little bit of history lesson. How did the instrument come about? What was the technology that was going on at the time? Who were the major players that led to the discovery and the implementation of the IC instrument? And we kind of related that to the company called Dionex and Dow Chemical Company. All right, so we're going to fast forward now because there's been some changes that has happened to the equipment. Those aren't necessarily important because if they were, we'd be here all day. So what we want to talk about are the major pieces and parts that make this thing up. All right, so I'm going to first start with this word chromatography. We keep seeing this word over and over and over throughout the course. And chromatography systems are very similar to each other with just slight modifications. That's really all that we have to worry about. So the good news to you is that if you understand GC, then this is kind of equivalent to IC as well. And that would be kind of equivalent to HPLC and to TLC. You're going to find some common trends with all chromatography, whatever kind of instrument that might be. So what do I mean by that? Well, the word chromatography, in terms of ion chromatography, number one, we need something that we call a mobile phase, right? A mobile phase is what makes this thing work, and it's what makes this thing separate, and we have to have a constant flow of it. So we're going to have to talk about the mobile phases that are required for the instrument, because even though it requires a mobile phase, just like GC did, that was helium, right? Well, this mobile phase has to be very particular. We also have to talk about the column. The column is where the separation begins to take place. In the terms of GC, you learned about silica columns, which are basically glass columns, capillary columns, versus the metal packed columns that we used to use back in the day. Well, those columns are slightly different for ion chromatography. So they look different, and they are made up of different materials, and they have different stationary phases on the inside of them. All right, so that's something else that we're going to have to take a look at, but you know, the heart of it is still there. We have to have a column, just like in GC, and we have to have stationary phase, just like in GC and TLC at this point that you've learned about. But they might be slightly modified, a little different, in order for ion chromatography to work out. We're going to also have to talk about flow rates. That's also something that's pretty important. We saw that really take part in gas chromatography, where we would go in and set flow rates of the helium gas that was coming through our system. The same thing's going to happen to ion chromatography. We have to talk about proper flow rates. We don't want to go too low. If so, we're not going to get a very good chromatogram. And we also don't want to go too high, because if we do, it's going to increase the pressure and things are going to start popping. So those are going to be problems for us, and we need to watch out for them, and we need to talk about flow rates because of that. And finally, detection. You know, everything has to have a detector. The GC had a detector. It had multiple different types of detectors, basically measuring whatever you want it to measure. We had a detector for pretty much everything that was out there. The same thing happens with ion chromatography. In the field of ion chromatography, we have to have a detector. What is that common detector that you might see on an instrument, and are there different versions of that detector that's out there that will allow us to expand our capability and measure other things that we maybe wouldn't expect to use an IC for? As far as ion chromatography goes, GC world, we said it's perfect for volatile organic compounds, VOCs, or things with lower boiling points, and especially things that are thermally stable. All right, well, what if they aren't? What if they do not meet that guideline? Well, that's one of the reasons that we have ion chromatography in our lab. So ion chromatography, as you would expect, will separate ions, and those ions, I'm also going to put / polar compounds, because ions, people think of something like just Ca+2 calcium, right? Or Cl- for chloride. The reason I'm putting polar here is because they don't necessarily have to be single cations or anions that you measure. So, for instance, CH3COO, that is acetate, and that is a complex molecule versus just the simple little ions on the left-hand side of the screen. But this thing is charged, and this thing can become polar, and this thing can go through the system and be detected out the other end as well. So over here to the side, what I'm going to write is I'm going to say, listen, ion chromatography can measure cations, which are positive containing species. It can also measure anions, which are negative containing species. And under these umbrellas, we can also do other things like organic acids. Organic acids are typically going to be anions because those hydrogens break off, leaving a negative piece behind. So I'm going to put a negative here. Now, not every single time, but most of the time they are going to be negative as far as charges go. We can also measure things like amino acids. Now we're kind of dabbling into a little bit of biochemistry and biotechnology, maybe. Carbohydrates is also a part of that. So sugars, for instance, can be measured on the instrument without a problem. Nucleotides. And these nucleotides are coming from things like deoxyribonucleic acid, or DNA. And that also, of course, would lead to proteins because amino acids can lead to polymers that we would call a protein. And nucleotides can come together and somewhat make peptide bonds. And those peptide bonds can basically lead to other things as well. All right. So we can kind of use IC for a number of different purposes. It's not just our chlorine and our calcium that we would see over here to the side. That's typically how people would train themselves, but that's not necessarily a requirement anymore in the laboratory field. Now, granted, it is what we would experience in our laboratory block that you're getting ready to experience, and that's just because these are very easy labs, easy sample prep, not a lot of things have to be involved, and it gets you working on the piece of equipment, which is how these laboratories are really geared. All right, so there's kind of the overview of ion chromatography, and what I want to do is I want to start talking about this very first one, which is going to be called the mobile phase. We want to take a look at the mobile phases, talk about how they're different, talk about maybe how they're special, and maybe things to watch out for in this system. So the mobile phase is going to be sitting up here at the top of the instrument, and most of the time it's going to be in a bottle that has a piece of tubing that goes down to the bottom, and then this tubing will typically go to the side and into the instrument at some point in time. So this mobile phase, of course, is a liquid. And the reason I'm saying that is because in gas chromatography, it was not a liquid, it was a gas, and that was helium. So this is one of the ways that this is going to be different. As far as the mobile phase goes, this is typically an ionic solution. What that means is that it is typically water with something dissolved in it. And that something dissolved is going to be, quote, a salt. Now, you're probably thinking something like NaCl. That's a salt, right? Well, it is a salt, but one of the reasons that we call that a salt is because it breaks apart in a liquid solution. So there's other things that also break apart in a liquid solution. So there's other things that are going to be classified as salts that are out there. NaCl is not the only one. So are we using salt in the ion chromatography system? And the answer is no. We're using other things instead, and we'll talk about what those things are probably in the next video or two. The problem that we see, and the reason that I mention this, is because these ionic solutions, these salts that are dissolved in water, these create ions. So you probably have heard me talk about this already, but what we have here is a detector at the end. And the detector measures ions. So if ions come into the system, then the detector is going to see them, and it gives us a positive signal on the chromatogram screen or the software screen. Well, you're thinking, okay, well, I've got a sample, and this sample has ions. And the ions, maybe we would have positive ones and negative ones. And these ions go into the detector and out the other end, and we get a signal. And the answer is yes, you're perfectly right. That is okay to say because that's exactly what happens But the issue here is that our mobile phase also have ions. So the ions from the mobile phase will also go into the detector and out the other end. And we've already kind of discussed this problem that Hamish really discovered back in the day when they began to play around with the instrument and the detection and the stationary phase and the mobile phase. This was one of the things that they had to take care of. How can we eliminate the signal from the mobile phase because it carries ions? So your very first instinct will be, well, why use the ionic solutions, right? Why can't we just use something like a DI water? And we've also discussed that too in the history lesson. We said that the water does a perfectly fine job. The problem is that it's the retention times. It doesn't really separate components from each other. So, for instance, the fluoride and the chloride. It was very difficult to separate these two because they both have a -1. And we need these to be perfectly separated. We need a peak for each and every one of them. And DI is going to be very difficult to accomplish that. So we use a little bit of ionic solution, a little bit of things that carry some charges with it, and that promotes the separation for us a little bit better. As far as the mobile phase goes, there's really two versions here that are the most common. The very first one that we're going to talk about is a bicarbonate mixture. And when we talk about the amounts that we use to make these mobile phases, they are really in milligrams each. I mean, super, super tiny amounts that get dissolved traditionally in 2 liters of water, because that's your traditional size mobile phase jug that sits up at the top of the instrument. This is typically 2 liters. Now, of course, you can do bigger ones if you want to. If it fits, then you're more than welcome to make as much mobile phase as you want. But normally those are 2 liters. So milligrams of stuff of each one of these into a whopping 2 liters of DI water. So what you're seeing is that we are putting ionic species in a mobile phase. It is breaking up. We are getting some charges that are assigned to those milligrams of bicarbonate and carbonate, but they are super, super tiny, super small amounts that go on here. And those really teeny tiny amounts are going to be very easy for us to clean up at the end of this process when it comes to the detector. The bicarbonate and carbonate, these ions that get released, for the bicarbonate, this is an HCO3 minus, and for the carbonate species, it is a CO3 minus 2. Okay, so this is typically sodium bicarbonate and sodium carbonate that we use, and the reason that we choose these salts is because they're fairly cheap and they're very low in cost. So we need the carbonate and bicarbonate to do the job. The bicarbonate and carbonate, as long as it's present, it will do the job that it's supposed to do. We can get those ions from a number of different chemicals that we can order from in a lab, and sodium just so happens to be the cheapest and the most common. So because of that, that is what we decide to use in our instrument. So sodium bicarb, sodium carbonate, milligrams of each one of these dissolved in 2 liters of a solution, and this frees up the bicarbonate ion, HCO3 minus, and the carbonate ion, which is CO3 minus 2. The reason that we use the combo and not just one or the other, well, as you can already see, what they're doing is that they are carrying different charges here, -1s and -2s. So the multiple charges will allow for better separation. We have a mobile phase now where the negative or the positives or the negatives will kind of hang out with the positives and negatives that match the particular type of magnitude of charge. So our -1s will hang out with all the other negative and positive ones. The -2s will hang out with all of the positive or negative 2s. Traditionally, this is what we would find in anion chromatography. And cation chromatography, of course, could have different types of mobile phases that are assigned to it, but here's just one example, and it is probably the most common example in the ion chromatography field. Something that I don't like, a lot of people will look at the HCO3 and CO3 and they don't really have a visual of what this molecule looks like. So before I stop this video, I just want to draw each one of these. So sodium is Na+. And then we have bicarbonate. So here's a carbon that's in the center, and this carbon has 3 oxygens that are assigned to it. In order for the Lewis dot structure, though, to work out, we need a double bond between one of the carbons and the oxygens. And then because it's HCO3, there's my CO3, there's got to be an H on one of these carbons, all right? So one of the oxygens will carry with it a negative charge, and that's why these things hang out together, right? We got the Na+, and we have this bicarbonate that carries with it a negative charge. And that's kind of the glue, the interaction between the two ions that are keeping them together. And we call that an ionic bond because there's 2 ions in play, and that's what's grouping them together. This molecule, NaHCO3, this molecule is otherwise known as baking soda. All right, folks, that's what it is. It's baking soda. So you probably have sodium bicarbonate in your pantry, in your kitchen at home. You probably have used sodium bicarbonate in your cooking if you're making cookies or cakes or some kind of muffin, and that's all that it is. And that's really all that we have in the laboratory too. We have a very purified version of baking soda that we are putting onto the instrument, and that baking soda is releasing my HCO3 group, and that is allowing some of these charges to separate on the inside of the ion chromatography instrument. The next one was Na2CO3. That was my sodium carbonate. So here we have our carbon, just like we had up here at the top, and we have 3 oxygens. One, I'm going to draw it a little different, but it's basically the same. 3 oxygens all the way around, and then we still have to have a double bond between one of them, right? The difference is that it doesn't carry with it the hydrogen because this is Na2CO3. There is no hydrogen that's there. That hydrogen has kind of replaced one of those sodiums in the prior structure. So here's CO3, and we have 2 sodiums, so Na+ and Na+, and because this oxygen's got a double bond with the carbon, this one does not and this one does not, this one carries a negative and that one carries a negative as well. There's no hydrogen that's sitting on the oxygen, so therefore this will free up and this will be a negative charged area of the ion. So here we see an ionic bond between the sodium and the negative there, and another ionic bond between the sodium and the negative there, and this by definition is kind of like a salt. So this is sodium carbonate, and this is what gives up my CO3 minus 2, and this gives me the combo of the mobile phase that I really desperately need in ion chromatography to separate the ions from each other. All right, so that's going to be your intro to mobile phases. In the next video, we're going to continue on with this discussion. We're going to follow through with the bicarbon carbonate, things to watch out for, how to handle it, and maybe some other options that are out there for you as well.